All right, Stephen, now's the time on the show where we talk about the LessWrong sequences.
It is.
Excellent. And this is the ones where we said that we're going to do more of a summarizing of what's in it rather than a really talking about it because there's a lot of graphs and also a lot of this is beyond our pay grade.
That's a good way to put it. Our first one here is classical configuration spaces. And when I was reading it, it's the first post that we've come across since we've started doing these that I had no memory of, which must mean that when I was first reading these in my, I don't know, early 20s, this is where I noped out of the quantum physics sequence and just skipped to the next one.
Neat. Okay.
And I still wonder at the wisdom of even having these as part of the official sequences, but I want to the official texts.
Right. Yeah.
This seems like this could have been buried with whatever some of the boring books of the Bible kind of
Right. The latter half of the Old Testament.
Yeah. The thing is, before we dive into the content of it, it's like what does this have to do with rationality?
We talked about this earlier.
Well, so that's it. If all it is reinforcing the idea that mystery is in your mind, not in reality, and confusion is your problem, not reality's problem. Like, I'm already sold on that. I don't need a quantum physics course to drive that home. But maybe I do. Maybe it's like that's something that I can say I believe and I understand, but like it's not until you really encounter a weird, mysterious thing or seemingly mysterious thing that it actually drives that lesson home. But I don't know. This doesn't feel like it makes me a better rationalist. So like, if we were doing these at the whatever Lighthaven Tuesday readings, and it's like, wait, do you use this in your real life? No, never.
Definitely this is not used, and I've seen a few people try to use it, and I think they are doing themselves a disservice, believing in quantum immortality or something. On the other hand, I do think it's neat to have a thing that you can point to be like, I have a high probability belief that this is actually true based on all my other priors that I know that are true, and yet I don't actually have much of a way to prove that this is the case. At least I certainly don't in my day-to-day life. I know that there's probably people who are working on the quantum frontier that could point to experiments or whatever that prove things or highly suggest things one way or another. But having a thing like this that is counterintuitive, and yet you can say, based on the evidence, this is a thing that I think is true anyway, maybe it's an interesting exercise to have, that you can put a conditional probability on something that you can't back up with vibes tell me that.
Yeah.
That you have to back up only with this is what the math comes out to.
This is what the evidence forces me to believe. And
yeah,
I can dig that. I think really just articulating that into a LessWrong post, I think would have been a better use of time than writing 20 posts on quantum physics.
Yeah, but that's the difference between like being told fire is hot and it'll hurt you and actually feeling something that's hot and having your skin burned. Like, no, the difference is drastic.
I was going to use fire as actually a better example than I think quantum physics, because fire is one of those things that like we all know what it is, but it's kind of hard to explain what it is. If a kid asks what fire is, you can say it's that stuff over in the fireplace. But if they ask like why, you're like, oh well, it's oxidizing something, and it makes heat that makes more oxidizing, and concisely explaining what fire is a fun problem. But and you said it's the difference between being told what fire is and burning your hand. I'm not doing any quantum physics experiments here. This is the difference between being told what fire is and then reading about the chemistry of fire, right?
Okay, that's true. Yeah.
If I could give you all the way down to the atomic level explanation of fire, I guess I'd be better equipped to understand what fire is, and I work with fire more in my real life. I think fire would have been a better, and that could have been knocked out in 3 posts, maybe, right? I guess I wanted to bring up the wisdom of actually finishing the the quantum physics sequences. I don't know if people are liking it or if you're liking it.
I like certain things because they are a challenge, even if I don't necessarily like them. I feel like this is one of those things where once we get through to the end, I'll be like, I finished that thing, despite the fact that it wasn't the best time.
If we want to sludge through the arduousness of this for the sake of doing something hard, climbing Everest style, then I'm here for it.
Yeah, and it's not like it's trying to get through all of Plane Crash, right? Like that would be so many words. This is, less than a dozen podcast episodes.
Less than a dozen. All right, I'm skimming through the rest of the posts here, and there's a lot left on this sequence. But
is there?
Yeah, I'm afraid so.
Is there 20 left in this sequence
I
because
will.
we do 2 per episode, sometimes 3.
Yeah, I think doing 2 or 3 will probably be a little faster. Let's dive in here with the classical configuration spaces.
Okay, well, there is a bunch of graphs, and honestly, the only way to really get it is to go and read it and look at it. And so I would encourage listeners to do that. But as a few bullet point summary of what is being said in this post, I would start by saying that he introduces the idea of classical configuration spaces, saying that you can represent the relationship between two numbers as a graph. This is something that I'm sure we're all familiar with because we often have a graph representing an x-axis and a y-axis that shows the relationship between two numbers, right? And those numbers can respond to a location, like, say, distance from the center of the graph, or distance from some other central object if you want to reference something in the real world. So the x-axis could be distance of particle A, the y-axis can be distance of particle B, and this now shows the state of the A and B particle system. The system being the location of those two particles as a single point. You just have one point on there, and it shows the state of the system because it shows where A is and where B is in distance from the object that you're using as a reference. And as the state of that system changes, the point moves around on the graph to correspond to that change. Does all that make sense?
Makes sense is honestly not like at the end of this post. Actually, I grabbed a sentence and I'm like, am I just stupid? Because I can't even. I was going to use the word grok, and I like it's the right word, but it just sounds gross. It sounds like a bodily function. But
Grack is so insulted now.
no, Grak is fine. Grok is different.
Oh, really? Like, Grok could be Grack's brother.
Could be. Yeah, he's got a gross name. No, I don't know. But no, so I followed the post to the degree of like, I could probably check the right answers on a multiple choice test after the fact or something. But like, I don't know, man. So I'm following what you're saying, but let's see if we can kind of power through these. The thing is, I have no idea how much we can convey with like the posts are about as dense as possible already.
Mm-hmm.
And so, summarizing them, like what is the takeaway from classical configuration space?
Well, we haven't even gotten near the bottom of the post yet.
Well, I know, but if we take it this slow, I guess that's what I'm wondering. Like, are we aiming to actually teach people what's in these posts? Because that will be like the longer, like, let's dive through each bit and try and articulate it, or are we just trying to say like, here's what this one was about?
If I say that the number on the x-axis represents the distance from center of particle A, a number on the y-axis represents the distance from the center of particle B, that makes sense, right?
Yeah, I can follow that.
Okay, and then if you have one point that shows where that has both, a single point in that graph would has both a y coordinate and an x coordinate, and so it would show you the distance of both particles.
Yeah, I'm with you so far.
Okay.
He opens with like the joke about just imagine n dimensions and turn n into 8. Boom, done.
Yeah.
And that's basically So I kind of lost it after maybe 3 dimensions. I still don't know what it means. Maybe reading more of these will help it sink in of higher dimensional space or whatever. But I can't picture more than 3 directions, right?
I can sometimes get 4, but that's hard.
I haven't taken enough drugs to do 4. I mean,
I don't think I could do it on drugs. I can only do it when I'm sober.
I wish you could explain it. Maybe we'll get there, but it's like because I can point up, I can point left, and I can point forward or backwards, right?
Yeah,
but
I don't know. Just imagine you could point in another direction.
I've pointed in all of them already, though.
I know. That's why you got to imagine.
Yeah. So I think that's the thing is that it is, as far as I can understand it, it's math. It's purely mathematical, which isn't to say it's not how reality actually is, but there's no way for me to interact with it directly in a way that I can intuit. There is no version of this like sticking my hand in a fire, right?
Probably
until we get some weird whatever quantum roulette machine or something, right? Like you mentioned quantum immortality earlier.
Yeah.
But anyway,
I mean, on the plus side, we were only dealing with 2 dimensions right now, just the x and the y axis.
Yeah. So then the next point here is you can create a third axis, time, to have a record of these changes. The point turns into a line, baby squiggly, that draws out all the places the point was over time. I follow that just fine.
Yeah, so the point is at one place at one time, and at a different time, one or both of the particles have moved, so the point moves to a different spot. And if you're tracking this on the third axis of time, then you can see the 2 places where the points are at the different times and the line between them as the particles were moving.
Yeah, no, that makes sense. So if the third axis is time on a 2-dimensional graph, that makes sense. I can picture a 3-dimensional graph, and then time being the 4th dimension. But
You don't got to bother with that yet.
not
Like right
yet.
now, we can still think with just the 3 dimensions.
Well, yeah, but then he goes on to say, like, you may have previously heard the phrase "time is the fourth dimension," but the diagram at the right shows that the evolution over time of a one-dimensional universe with two particles. So time is the third. The first dimension
Hmm.
being dimension. Excuse me. The first dimension being the position of particle A. The second dimension being the position of particle B.
Hmm.
So that's all fine and dandy. In that, but I couldn't I couldn't properly absorb the rest once we get past three. But let's see if we can get through this, and maybe I'll learn more by the end. So
Okay. Right now, we're talking about these. Both these particles could be any place on the line, right? Any place between 0 and, let's say, the graph goes to 100. But let's say that there's some places that the particles can be, and some places that they can't be. Like no matter what, particle A is never going to be between 50 and 75. You could shade in on the graph all the places that don't include 50 through 75 to show all the places that the particle could possibly be, and just leave between 50 and 75 blank, since you know it'll never be able to be there, right?
yeah,
All right, cool. Now also imagine that like it isn't a uniform probability that it could be in any of those places. There's some places where it's very likely to be. Like maybe particle A really likes to be around 25 for some reason. So you shade that in like really dark, and the farther away you get from 25, the lighter the shading is to represent that it is less likely there. And then obviously between 50 and 75, it's completely blank. And then for some reason, post 75, like there's some chance it could be there again. So then you shade it in lighter over there, light gray. So you can kind of imagine that too, right?
yeah. This part I'm still on board with.
Okay.
And it's easier to see with the graphs in the post that he kind of hand drew, which also he has great handwriting. Like, I mean,
Yeah.
it's not whatever the I don't know refined whatever stuff, but my handwriting is abysmal, and his I don't know I it looks like whatever a font.
Hmm.
It's not really the point of the post, but I kept looking at these hand drawn graphs and thinking, damn, that looks pretty good.
Yeah. It's impressive.
Yeah, look, a little squiggle on the bottom of the B. Like that's clearly, he lifted the pencil. This would make sense if anyone listening could see my handwriting. It's actually embarrassingly bad.
Okay. So then we remember that we have the third dimension, the time dimension, and if the probabilities might change, like maybe at time 1 there's a really high chance that it's at 25, but at time 2 there's a really high chance it's at 35. And so between time 1 and time 2, the darkly shaded bits move from 25 to 35, and so it kind of looks like there's a changing in the shading over time. Like it looks sort of like a cloud with the darker bits moving at a diagonal. Does that make sense?
Yeah.
Okay. If the parts that it can't be change as well, then maybe the blanked out places start to look more like holes that are tunneling through the gray cloud rather than just, one block space where it can't be.
Yes. I can follow that too.
Okay. That is the majority of this post. There's a caveat that at the probability at any given time should be 100%, so that if some areas are really dark, then other areas will have to be really light. You could have like a very large shade of medium, a very large field of medium shade, or like a very small area of very dark with a large area of pretty darn light to make up for it, and all sorts of combinations in between. But like the total probability should add up to 100.
Right. The particle or particles are going to be somewhere in this area with
Yes.
some increased probability of, one place over another.
Yeah. So if the probability in one spot is 50%, then over everywhere else it has to be 50% totaled up. So it's going to be a lot less dense everywhere else,
Right.
and a lighter shade in our coloring in. Okay, and then the final point is that the laws of physics is what determine how densely these various places are shaded in, and how that changes over time. How the shape and the density of the shading in changes over time.
Yeah. I think that this is all something I'm able to, I think, intuit enough to follow.
Okay,
It's
that was the purpose of the point of the post.
Well, that's good. I mean, like, but there are definitely sentences in here that I just couldn't even finish reading before my brain stopped working.
Hmm.
And I'm pretty sure that the way that I'm imagining this in my mind isn't the way. Well, it's obviously not the way it actually is because I'm not a quantum physicist and I don't understand this yet. But I don't even think like the vague analogies I'm using in my head are appropriate. But that's what I'm running with. So like so far my mental model and like analogous tie-in hasn't broken yet,
Hmm.
but I think it definitely will when there's a gazillion particles, or maybe not. Maybe this will be fun since I never finished this sequence. Maybe it will tie together at the end in a way that like, and this is how like now you can intuit why, I don't know, when you pick something up, you actually lift it off the table or something, right?
Yeah.
If there's something like that, that kind of cool thing at the end that makes it make sense in a way that I can actually relate to, That'd be cool.
Well, let's see what happens when we get to the end of Feynman Paths.
All right, let's do it.
To your point, when you said you had a hard time visualizing more dimensions, you can, if you want to track more particles, you create more dimensions in this graph, which is, not a thing that humans can visualize. It's more of a math thing. Right now, we're just thinking of these two things because we can still visualize that.
Right.
This is my simplification of the post. If people who have a better understanding of quantum mechanics come back and say, Ineash, you totally fucked up by oversimplifying, and that's not what this means, please let me know.
Yeah, I mean, I think it's an understandable mistake if you're wrong, but that's the best summary I could come up with of the post as well. I think that's a good summary. And before we jump on to Feynman Paths, though, we've got to visit the quantum arena.
Yes. Okay. In quantum physics, particles aren't separate, so the graph gets kind of funky. Because right now we're talking about particle A and particle B, and like A can be at 1 and B can be at 10, or B can be at 1 and A can be at 10, and that's two different things. But in quantum physics, particles aren't separate. Like particle X at 1 and particle Y at 10, and then particle X at 10 and particle Y at 1 doesn't make sense to say. Like, you just can't say that in quantum physics. It's impossible. You can just say there's a particle at 1 and a particle at 10. There is no particle X or particle Y. That's a single case, not two different cases. That means that the graph kind of folds over on itself, and the overlapping little area in the middle where what used to be just one large path, where it folds over and goes over itself, that's where we get weird quantum effects that make sense mathematically but are not human intuitive.
I wonder, and I'm sure that he thought about either explaining the math and trying to make everyone sufficiently mathematically competent to follow this. I'm curious to see how we're going to get much further without the actual math.
I think the actual math we covered in the last episode, or possibly 2 episodes ago, I think it was the last episode, where we talked about complex numbers and how they will cancel each other out. This is how amplitudes can cancel each other out or reinforce each other. That's what's happening in that weird little overlap area.
That's a really good connection, and I think you're right. Not to pin us down or drill you on this, but so we've got two particles, let's say, particle X at 1, particle Y at 10. He's saying that it doesn't make sense to say, well, or it could be particle X at 10 and particle Y at 1.
Right. It's impossible to say.
And that's because that it's impossible to, in principle, tell the difference between particles?
Yes.
Okay.
Yeah, you can't tell apart particles. There's nothing differentiating them.
Right. They're fundamentally indistinguishable.
Yeah, there is no little tag that says one is X and one is Y. There's just a particle here or not.
Okay. That makes sense. I think I misread the next sentence, because then he says it's impossible to say, in fact. It's just, quote, there's particle 1 there's a particle at 1 and a particle at 10. That's a single case, not two cases.
This is me saying this, by the way, not him. It's my summary.
Oh, great summary then. Because that makes sense. All right, I'm following you.
So that is one thing that makes the quantum arena difficult. Another thing that makes the quantum arena difficult is that in the previous post, when we were talking about the classical arena, we used a single dimension to describe the position of a particle. It was just, X number of units away from the center. In quantum physics, a single particle takes 3 dimensions to represent, because you get one for the location, like we were doing, but you also have 2 more dimensions to represent the amplitude. One is for the real number part of the amplitude, and one is for the imaginary number part of the amplitude. Because if we remember from a episode or 2 ago, the amplitudes are always represented by complex numbers, which have a real number and an imaginary number part.
Right.
And each one will take a dimension to represent. I do not know why personally, but that is what you need to represent them.
Yeah, that's kind of where I'm at. Is it basically, all right, I'll take your word for it, but it's not. I can't. Maybe this is explained more later, or maybe it's just because none of the sequence content is supposed to be like, well, now that I've said it, you believe it.
Right.
It's never supposed to be like that. Mm-hmm. But I still don't understand why that's the case. Why there's 2 dimensions for the amplitude, one for the imaginary and one for the real. It's more just like, all right, I guess I'll take your word for it because you seem to know what you're talking about.
Well, entirely by coincidence, last week on my Twitter, I saw someone asking, why is there an imaginary number portion of amplitudes? Someone answered with a link back to Scott Aronson's blog. Scott Aronson is a quantum was a quantum computer expert, and he talks about the various ways that this can shake out and how you always get back to an answer that involves imaginary numbers. I started reading it, And I got a few paragraphs in before it got to the point where I could not understand and could not follow anymore. But it looked very interesting, and it looks to be the kind of thing where, like, if someone wanted to sit down and study this, someone, of decent intelligence, and like dedicate a month, maybe 2 months to just, several hours a day reading and studying this, they could get it. On that basis, I am trusting that this is not just like, now you have to believe me, that you can actually go forth and verify this for yourself. I just do not have the time or inclination to do that. But it was really interesting reading Scott Aronson being like, and then I was doing this, and entirely by coincidence, I came back to the same configuration. I was like, oh my God, this is actually inherent to the things. And I was like, neat.
That is cool. And yeah,
Yeah.
he knows his stuff. I think the issue is like there's just so much to get that you need for foundation before you can get up to where, at least for me, where I can get up to be able to follow this conversation. I've listened in and participated in conversations that like the majority of it is way over my head, but this is like almost all completely over my head. If Aronson or Yudkowsky were to say something egregiously wrong, I wouldn't be able to call them out on it. And
Right.
And you said something about going out and like checking for yourself. There's no way you and I will ever do this.
Exactly.
Like unless we get to play with a particle accelerator or something, right? Like it's like us verifying the age of the universe. It's like I'll take Neil deGrasse Tyson's estimate as my current best guess, right?
Yeah.
I'm not gonna. There's no way I could come up with a better one.
I think honestly that's kind of the point of going through these posts right now, at least for me, is I'm taking it kind of on faith, like on a provisional. I have a good reason to trust these people and to think that other people have verified this level of faith, that this is all mostly correct, especially for the time that it was written, and that I'm just going to do my best to take the parts I can't understand on faith and get to what they're actually saying and trying to summarize it. If you want to really know it and really make sure that it's true, then yeah, you're going to have to put in the work. But if you're like me and you just want to read these sequences and you want to know what the sequences are saying, I think that's kind of what we're doing here. Like when we laid out what classical configuration space is trying to say, that like you're basically trying to imagine these graphs that are shaded in based on how likely it is for a particle to be somewhere, and that the laws of physics are what changes which parts are shaded in how much. Like that's basically the point of that post, and I think we managed to cover that. And if someone says like, how do you know that, I'm like, well, okay, you can go do your research, but that's what the post says.
Fair enough. I was, and I realized I took us a bit far afield, not talking about the content of the post and kind of meta commentary, but my initial secret goal of going into this conversation was talking you out of finishing this sequence. And,
Okay.
but I think you made a compelling case, and yeah, there's like 23 of these left.
Oh, you counted just now?
Yeah, so we've got some left, and then of course like some others are like parts of multiple sequences, and so it shows up a bit later, but it'll be an odd couple of months for the sequence posts, but I'm down to keep going if you are. So let's keep rocking and rolling.
Okay, I'm gonna do my best for as long as I can,
and I'll try to bring more to the table next episode.
Oh, okay.
Yeah, rather than
Rock
just
on.
have you have to teach me, because to be perfectly honest, I gave up reading these again. Apparently, I guess I gave up like 15 years ago, and I gave up this time because
Well, at least you're consistent.
I couldn't really just figure out like, why is this worth the effort? Like some of the sequence posts are difficult to understand, but then when you get it, you're like, oh, that's so fucking cool. With this, I get it. I'm like, okay, my head hurts a little less now, but like I don't feel any smarter for having for having learned this. Maybe there's some payoff, and maybe there's not. But I'm with you. Let's roll through it.
Whew. Well, let's see, where were we? And a single particle takes 3 dimensions to represent instead of just one, because there's real number part and imaginary number part of the amplitude. Okay, so we're talking about the amplitudes and their distributions in quantum physics. I pulled this out of the post directly, that laws of physics describe how amplitude distributions develop into new amplitude distributions. They do not describe, even in principle, how one configuration develops into another configuration. You can't possibly break it down into the evolution of individual configurations. And what that means is that it doesn't describe how like a particle goes from one place to another place. That is the configuration. The laws of physics cannot describe that. They don't describe that. What laws of physics actually describe is how those clouds change in density over time. The amplitude distributions, how the real number part and the imaginary number part of the amplitude change over time. rather than where the particles actually are. One of the interesting parts about all this is that the behavior of each of these amplitudes depends on the amplitudes at neighboring points. So you can't figure out what happens at an amplitude just by looking at that one point. You have to look at what's happening nearby it too. The analogy he makes is like in Conway's Game of Life. If you look at just one cell, you're familiar with Conway's Game of Life, right?
No, actually.
Oh, okay. It's just a straight grid of cells. One
Oh
by one
yes.
blocks.
Okay, no, I am familiar with this. The old school. Yeah, this was like an old evolution little thing it was like an old school computer simulation.
Yeah,
Yeah.
where like a cell is either on or off, and if it's on, it's like it's filled in. And then the rule is a cell either stays on or turns off, or if it's off, it either stays off or turns on based on what is happening to cells around it. Like if there's 3 cells on around it, then it turns off. Otherwise, it turns on, something like that.
To dive back into the post, before he mentions Conway's Game of Life, he mentions being confused by the first time he saw the Schrodinger equation.
Mm-hmm.
And just to reaffirm to myself that I'm not crazy, I went ahead and went to the Wikipedia page of that. There's fewer letters and numbers in this equation than I've ever seen in anything else. Like it's all squiggles. It must be Greek letters.
Okay.
But good God, like so, this is just reaffirming my kind of sanity check that I predict, and I'm not gonna like I could obviously force the outcome of this, but I don't think I'll understand quantum physics at the end of this because I won't unless he shows this equation and breaks it down. But yeah, let's see what happens.
Okay, so back to Conway's Game of Life. It's like asking what's the future state of this one cell without looking at the cells around it. Like the immediate future of the cell depends on its neighbors, and the distant future of the cell may depend on distant neighbors. Bring this back to classical physics. In classical physics, you know the position of particles separate from its momentum. You can know exactly where it is, but not how fast it's moving. In Conway's Game of Life, however, the velocity of a glider. Do you remember what gliders were?
In Conway's Game of Life?
Yeah.
I mean, if you click the link, it takes you to the Wikipedia page and has little animations. If it's the thing that's moving across the screen, then yes.
Yeah, they're like artifacts where cells were turned on and off in a pattern that over time looks like a little object like moving in one direction at a given rate of speed, and it just like keeps going along and it keeps maintaining its shape, and it's really cool. But it's just a pattern of turning on and off in a sequence.
Right.
And in Conway's Game of Life, the velocity of the glider isn't like an additional separate fact about the board. These cells are just either alive or dead, and the motion of the glider is like it's an apparent thing that arises from the configuration repeating itself and how the cell rules are applied. It's not actually a thing that's moving, right?
Yeah, totally with you. That makes perfect sense.
Okay. That is what he's saying basically is a similar way to think about quantum amplitudes changing over time. There isn't an individual particle that has a momentum. It is the result of individual amplitudes shifting over time, and it looks like there's things that are moving, but it's amplitudes shifting instead.
Right on.
You start with a blob of amplitude centered on position x, and at time t later, it has evolved into a similarly shaped blob at position x plus d. Then way up at the human level, it looks like a particle moving with velocity d. But on the quantum level, there is no like thing moving at velocity d. It's just amplitude distribution changing positions over time.
Yes.
Okay.
I'm following it. I can kind of see the analogy. I'm playing with. There's an interactive version of the Game of Life on the Wikipedia page, and it's funny if you let it run for like just I don't know if it generates randomly if you restart the page or whatever, but it runs randomly like quickly through 1,000 generations, and then it's just 2 flickering things that are left. And so I clicked a few cells, and now it's all freaking out because I've got a bunch of those gliders, and it's moving instead of like 100 generations every couple seconds. It's really like a generation every half second. Like it's clearly struggling at this point.
But each individual cell doesn't move. It just changes from on to off.
Right.
And that's similar to how like amplitudes just change in their density rather than things moving.
Okay. I mean, yes, I with you. I follow it. I'm just waiting until I can relate this to something I can touch, but I don't think that this is where this like that's not where quantum physics ends up, as far as I understand it. If it did, someone would have told us by now.
Right.
But if anyone could tell us, and this happens to just be a perfect segue, it would be Richard Feynman.
It would. He starts off by giving a example of a mirror, and when light hits a mirror, it reflects off at the angle of incidence always, which is what we see up here on the classical level. People say, well, why should that be? And actually, down at the quantum level, every part of the mirror reflects a particle at every angle, which is just bizarre to think about. If every part of the mirror were to reflect a particle at every angle, then like I don't even know what you would see necessarily when you look at a mirror. It
Solid
is
white
very
light.
hard for me to imagine. Yeah, maybe. Like I'm not sure what I would get.
So this is fun because actually, saith Feynman, each part of the mirror reflects all angles. So why is it
Yeah.
that way up at the human level, the mirror seems to reflect with the angle of incidence equal to the angle of reflection?
Well, as we said earlier, all the particles have amplitudes. Those are represented by both a complex and imaginary number, and these amplitudes change with time. So the longer it takes for a photon to get from one point to another, the more the phase changes. And the phase changes of the amplitude are cyclical, so that after some time t, a phase is exactly the opposite of what it was at time t1, and then at time t3, it's back to where it was t1, which is opposite of where it was in t2. So you can kind of think of it, Feynman says, a little clock faces with the hands spinning around and pointing in like, vaguely similar or dissimilar directions and opposite directions at times, and then coming back to pointing in the similar direction again. So the longer the path a particle takes, the more phase change it has. So the further the paths go from the center, the longer they will be, and the more the phases will change from the shortest one and start canceling each other out. Whereas the paths that are closer to the center reinforce each other. So he says a photon, which can get from S to P by striking any part of the mirror, will behave pretty much as if it's only striking a tiny part of the mirror, that only a tiny part of the mirror exists, the part where the photon's angle of incidence equals the angle of reflection, because all the other ones get out of phase enough that they cancel each other out.
Great. Yeah, I'm liking this. It's as easy to understand as everything Richard Feynman says, which is to say, like, not that easy, but easier than anything else that I've ever heard anyone explain physics.
Yeah.
Certainly this level of physics.
Right.
Like, it wasn't until I read some of the Feynman lectures that like I could understand on an intuitive level why blowing on a spoonful of hot soup cooled it off.
Yeah.
And I'm finding this to be equally elucidating.
Okay. The idea that like when the arrow is slightly off in one direction, slightly off in a different direction, they cancel each other out, which is why the 2 points on either side of the center will cancel each other out. That kind of makes sense.
Yeah, I mean, again, I still am stuck with like this doesn't impact real life because like the way it sounds is like I should be looking at a mirror and seeing little flickers. If it only pretty much behaves as if it's doing what it intuitively looks like it's doing, you would think that sometimes you'd notice little changes. But I guess a single photon is like next to nothing, right? So
yes,
it aggregates to look like it's doing what it naively looks like it's doing.
Right.
But,
And
underneath all of that, there's this whole mess.
I think every direction aside from the center one cancels out slightly, and the further out they are, the more they cancel out.
And I think it could also be that if it's moving slightly, if it's canceling out slightly in one, or if it's moving slightly in the wrong way, it's probabilistically also moving the other way, and those cancel out.
Yes.
And all you're left with is the one that's going straight.
Yeah.
Okay.
The really interesting part about this is that he says actually you can manipulate the mirror if you know this sort of thing. You can selectively scrape away bits of the mirror so that distant parts don't cancel out anymore. The quote is, you can make a mirror that reflects with the angle of incidence not equal to the angle of reflection. It's called diffraction grating, but it reflects different wavelengths of light at different angles. So a diffraction grating is not quite a mirror in the sense you might imagine. It produces rainbows of color, which, how fucking cool is that?
It's pretty cool. And
Yeah.
that's, I guess, what I might expect to see rather than flickering of whatever different parts of the mirror's image being reflected. I guess it would be different wavelengths of light. Okay, cool. I'm with you so far. So how fast do the little clock face arrows rotate? And that's as fast as the photon's wavelength, which is what a photon's wavelength is.
Yes.
Which is kind of fun to think about. This is the Feynman shit I'm talking about, right?
Yeah.
It's like, okay, I get that. That's awesome.
Yeah. It says the wavelength of yellow light is 570 nanometers. So if yellow light travels an extra 570 nanometers, the little arrow will turn all the way around and end up back where it started. That's what wavelength means. It's kind of awesome.
Yeah.
So, key to redriving the classical hallucination, which is the world that we live on, is that most of the possible paths cancel each other out, and only a tiny grouping of neighboring paths add up. So, most of the amplitude comes from a small neighborhood of histories. Now, the reason we got the crazy results from the earlier experiments was that they were extremely small and very discrete, and we could fuck around on these tiny nanometer levels. But by the time you climb up from a few hundred nanometers to the size of human beings, most of the amplitude contributions have canceled out, except for just a very narrow neighborhood around one path through history. And that's why things look like the way they do.
That's pretty fun. It's also one of those things that like you just take as a given in science fiction or whatever. Like when someone shrinks down to the size, like Ant-Man, perfect example.
Mm-hmm.
He goes subatomic, right?
Mm-hmm.
But there's still colors,
Right. Which
and
there would not be.
there wouldn't be, right? You're now smaller than the things that make colors.
Yeah.
But you just it's intuitively it sounds like you should be able to do that, right? And
Mm-hmm.
that's why no one really cares, because also you're not supposed to take it as as serious as whatever real science fiction. That's just Ant-Man's just fun. But
Mm-hmm.
yeah, when you get that small, everything's black.
Yeah. And there is one final note here about why the classical hallucination looks exactly how it does. Massive things are more energetic because mass is just a form of energy. So the more massive something is, the more energetic it is, and the faster the little arrow rotates. And compound objects, like neutrons made of three quarks, have a collective amplitude that's the multiplicative product of the component amplitudes. You can treat a neutron as an individual. So by the time you're moving up to a human being, which has, I have heard, quite a few neutrons within it, the mass energy is really extremely large relative to a yellow photon. And the clock is rotating extremely fast, which means the wavelength is extremely short, which means that the neighborhood of paths where things don't cancel out is really, really, really narrow. A human experiences what seems like a single path through configuration space, which is the classical hallucination.
I'm glad we did that third one, because that did kind of drive this home. I'm no closer to being able to rederive the Schrodinger equation, but I better understand the last two posts.
I'm glad that this post exists because the idea of like if everything is a waveform over everything, why don't we all feel like we're just blobs of probability going through everywhere was a thing that bugged me for I think up until I first read this post.
And that's why I like the guy and man who stares at goat or men who stare at goats, couldn't walk through a wall, right?
Right.
And because in when you get half of the explanation, it sounds like, oh, it should work some of the time, right?
Mm-hmm.
But and some of the time is like, yes, if I could run the universe for a Google years, there's a chance that you might be able to push your finger partway through a wall or something, right? But
I think
like,
even at that point you wouldn't. The energies involved are so much that that would not be enough time to get a path that wouldn't cancel out.
okay, so maybe that wasn't a high enough number. But if my understanding is in the right direction, there is some number where like it's not physically impossible, right? It's just practically
Maybe
impossible because it will never happen, on any observable time scale.
maybe once you have as many years as you have dust specks that landed in people's eyes.
three to three.
Yeah.
All right.
Whatever that triple power notation was.
Yeah. Well, awesome, man. I'm glad thanks for helping us get through this. So next week or next episode, we've got no individual particles and identity isn't in specific atoms.
Yes. And I think those two are significantly shorter, but should be easier.
And I think those are already things I kind of already understand. So I'm looking forward to getting the confusing stuff laid on top of it. But at least I'm with it so far. So
Hell yeah. I'm hoping this was one of the harder chunks that we got through, but we'll find out.
I think it was, at least certainly so far. But yeah, I think it laid the complicated groundwork, and you're doing a great job of tying it back to the previous posts. So
Alrighty.